Today we're going to start talking about linear transformations. Before you watch the rest of this video, if you haven't already watched it, I highly recommend watching this video here from 3 Blue 1 Brown. In this video, he does a really good job of explaining what linear transformations are, and he does it with some really nice graphics and visualizations. So that's 11 minutes well spent. If you got the PDF up, you can click here. If you don't, it's pretty easy to find on YouTube. So let's go ahead and look at images and preimages. This whole part here is really, a good bit of it is just vocabulary. So suppose we have a function that takes in a vector from R2 and it outputs a vector from R3. We denote it by this right here. Now this notation is read as f maps R2 to R3. So R2 is the domain of the function and R3 is the codomain of the function. You might have expected me to call that the range, but we'll talk about range in a minute. So suppose that this particular f is given to us by this down here. F of x equals, or f of xy equals x plus y, x minus y, and x plus 2. So to do f of 1, 3, what we get there is, let's see, the first entry is going to be 1 plus 3, which is 4. The second one's going to be 1 minus 3, which is negative 2. The last one's going to be 1 plus 2, which is 3. Let's do f of 4, 1. First entry is going to be 4 plus 1. The second entry is 4 minus 1. The last one's going to be 4 plus 2. So it's really just, a multivariable function. So a couple of words here. We call this 4, 2, 3. Since that's what we got by applying the transformation to this, we call 4, negative 2, 3 is the image of 1, 3 under f. And 1, 3 is a preimage of 4, negative 2, 3 under f. Now, if f is a function, anything that you input to it is always just going to have one image. But it's possible that a point over here in the codomain, it might have more than one preimage. That's the reason I said is a preimage. Now, image and preimage, we can use those here, but you can also go back and use them with just regular old functions. I'm going to zoom in and just talk for a second here. Normally, if you had the function f of x equals x squared, it would typically be written out like that. But using this new notation, you could write it as f maps the real numbers to the real numbers. And it's defined by this up here. So defined by f of x equals x squared. And just, you could say something like f of 5 is 25. You could say 25 is the image of 5 under f. And 5 is a preimage of 25 under f. And again, I said it's a preimage because negative 5 is also a preimage of 25 under this function. So notice the reals, the set of all real numbers, that's both the domain and the codomain. The range of this is going to be the non-negative reals. And you can think of that if you graph it, it's a parabola that goes up forever on both sides. So the range is going to be all the non-negative numbers, but the codomain is still just R. All right, so let's go down here and look at another example. Here we go. F maps R2 to R2. Let f maps R2 to R2 be defined by this function here. Find the image of 3, 7. Okay, so x is 3 and y is 7, so this is going to be 3, 10. Okay, now find the preimage of 4, 3. Okay, to find the preimage of 4, 3, what we would say is x equals 4. Basically what we've got here is 4 and 3. Let me write this out a little better. So find the preimage of 4, 3. That means that x plus y is equal to 4, 3. And so that gives us immediately from here 4 is x. And from the other one, 4 plus y is 3. So y is going to be negative 1. So that's the preimage. I could write it like that, or I could write it as 4, negative 1. Probably makes more sense to do that right as a point. Okay, what's the range of R? Well, using this, we could get any point we want. So the range of R is going to be all of R2. And I didn't explain that very well. We'll talk about that more later. Don't worry too much about it right now. Okay, let's look at this example. Let G map R2 to R2 be defined by this function. G of xy equals x0. This is an example of a projection. And you can think of this as being a function of like casting a shadow. It maps any point in R2 to the point on the x-axis directly below it, or above it if it happens to be in the bottom half of the plane. So like right here, find the image of 1, 2. Well, it's easy enough to just say, well, x is 1, y is 2, so this is going to give me 1, 0. So if this was the original point, the image is going to be down here. Now this next part says find the image of the line segment from 1, 3 to 4, 2. All right. We'll talk about this more a little bit later, but if you're finding the image of a line segment, let's see. What you can do is you can find just take the image of every point along the line. So let me draw that. I'll just do it on here in black. The point 1, 3 to 4, 2. Actually, I'm going to redraw this. So 1, 3, that's going to be here. 4, 2 is going to be here. And so what this is going to do for each one of these points on this curve, or on this segment, it's going to map it to the point immediately below it. So this is going to get mapped down to here. This will get mapped to here, and everything in between is just going to come straight down. So our image is going to be this over to here. So the image is that whole line right there. And notice the image of the endpoint, image of 1, 3 is 1, 0. Image of 4, 2 is 4, 0. So if you want to, you can draw little arrows here. Like that. And then everything in between just also goes down. Okay, what's the range of G? I made a small mistake here. It doesn't really matter, but I call this F, but it's actually G. Okay, what's the range of G? On this one, you can tell, I think, pretty easily. The only points you're ever going to get are the ones that lie on the axis. So what's the range of G? We can say this a few ways. The points on the x-axis. That's one way to describe it. Another way we could describe it is multiples of, or better yet, the space spanned by this set of vectors. Set only contains 1. 0, actually no, it should be 1, 0. So basically what we've given there is a spanning set, because that the range of this thing happens to be a vector space. We could also say the set of points x0, where x is a real number. This is called set builder notation. And yeah, it means all the points x0, where x can be any real number we want. So that'll get us all the points that lie on there. Okay, what about this next one? Find the pre-images of 3, 0. If you come over here, I'm going to mark that in green. 3, 0 is this point here. And if you look at what gets mapped to that, everything above and below it. So the pre-images of this are going to be everything straight above it or straight below it. So probably the easiest way to say this, I'm going to do it two ways, in English and then in set builder notation. First up, the easiest way to do it is to just say the points with x coordinate 3. You could also say the set of points (3y), where y is any real number. So either one of those are perfectly good ways to talk about the pre-images of 3, 0. All right, we'll talk about definition of linear transformation in the next video.